Okay. So last time I was talking about Laplace's and Poisson's equation and showing how to solve Poisson's equation in free space using a Green's function. So now there's certain interesting properties of harmonic functions. And a harmonic function is a function u that satisfies Laplace's equation. So Laplacian of any harmonic function is 0. Okay, so the first property is the mean value property. Which states that a u is harmonic, then u is equal to its average value over a ball, whatever ball of radius r that is centered at x. Well, here either the boundary of a ball or the average value over the entire ball, so including the interior. Okay. So here we have, in however many dimensions we have, some ball that is centered at x and has a radius r. So the interior is b of xr, a ball centered at x with radius r, and then the circle or sphere or whatever shape you have, that's its boundary, is the boundary of b of xr. So you can either examine the values of u throughout the entire ball, and that's this integral, take the average value. So here the absolute values are again used to indicate size. So this would be like the volume of the ball in this case, and this would be like, think of it as surface area in the case of size of the boundary. So if you take the average value of u either on the interior ball or the boundary of the ball, u is equal to those averages. Now, one interesting consequence of this is, suppose that u is known to be, as in ck, which from last time, it means that it's k times continuously differentiable. Then what happens is u turns out to be equal to its own integral over an appropriate domain. So an integral of a function is always 1 degree smoother than the function you're integrating. So because u is equal to its own integral, because it's ck, the integral of u, which is also u, is in ck plus 1. So if you take that to its logical conclusion, so basically by an inductive argument, you would see infinity. So it has continuous derivatives of all orders. So harmonic functions are infinitely smooth. A second property that actually can be proven from the mean value property is maximum principle. So the maximum principle is, let's suppose that omega is a bounded domain. And we have the weak maximum principle, which says that if U is harmonic on omega, then a maximum of U on, as here, when I have omega bar, that's the, called the closure. When you're applying a bar to a domain, the closure of a domain is equal to the domain itself union its boundary. So for instance, in one dimension, if you have an interval, an open interval, then the closure of that interval will be the interval as well as its endpoints. So in other words, like less than becomes less than or equal to. So the maximum of U on the closure of omega has to occur on the boundary. So you cannot have a situation where, if you look at omega over all of omega, that has some absolute maximum in the interior, that maximum value has to occur on the boundary. Now, this might lead to the question, okay, so maximum value has to occur on the boundary, but can there be a tie? Like, can you have a maximum value that's assumed on the boundary, but that same value is also assumed at a point in the interior? And that takes us to the strong maximum principle. And what that says is, if there exists some point in omega such that the actually, I want to exclude the boundary in this case. So omega subtracting out its boundary, so we're only dealing with the interior. So if there's some interior point of omega such that U at that point is equal to the maximum over the whole domain including the boundary. So in other words, if we have a tie, maximum value is assumed on the boundary and interior point, then U must be a constant on all of the closure of omega. So, in one dimension, a situation like here's an interval, and let's suppose a maximum occurs here at an endpoint, and then it hits again, and it goes from there. So this is not allowed. A harmonic function cannot behave this way. All right. Now, some interesting consequences.
So it means that it shouldn't hit inside the
it can't hit inside like at a single point. If it does, then it has to hit everywhere and therefore be constant.
Okay.
Okay, so here's some ramifications of the maximum principle. First, you also get a minimum principle. So everything that's said about the maximum applies to minimum. And the reason is you just replace U with minus U. Because if a function is harmonic, then if U is harmonic, then minus U is also harmonic. And then, if you put the two together, maximum principle and minimum principle, the Dirichlet problem Laplacian of u is equal to 0 inside the domain, and then u is equal to some function g on the boundary. So just Dirichlet boundary conditions for the whole boundary has a unique solution. And the way you can see that using the maximum minimum principle is, so I've got a quick proof, u1 minus u2, so these are two solutions. So in other words, proof by contradiction. You assume that you have two solutions. You look at their difference. So the difference of two solutions also satisfies Laplace's equation, but they satisfy 0 on the boundary, because for both solutions of the same Dirichlet problem, therefore the difference is equal to 0 on the boundary. But since the minimum and maximum values must be assumed on the boundary, then it must be 0 everywhere. So u1 has to be exactly equal to u2.
What is that G-shaped thing?
That is G.
Oh, okay.
Yeah. So I'm glad my G is G-shaped.
Why is it a G? Is that?
I just picked a letter.
Okay, so it just means it's a constant.
Yeah. Well, it's just some function.
Some function.
Yeah. Okay. Now, that's the Dirichlet problem. But what about the Neumann problem? So the Neumann problem, actually, this is back to Poisson's equation. So I have minus Laplacian of u is equal to f in a domain, and then normal derivative du dn is equal to some function h on the boundary. So it turns out that the solution to this is not unique. And the reason is, if u is a solution, then you can add any arbitrary constant to that solution and still have a solution. And the reason for that is, what are the conditions that u is supposed to satisfy? They all have to do with derivatives. So when you plug this into here, that c is going to go away anyway. So you have basically one parameter family of solutions, and they all differ from one another by a constant. But there's actually a situation in which a solution would not even exist. Because if I look at the integral over omega of f, so your right-hand side of your Poisson's equation, well, f is equal to minus Laplacian of u. But Laplacian is equal to the divergence of the gradient. Now, by the divergence theorem, also known as the Gauss divergence theorem, the integral of a divergence over the interior is equal to the integral of a normal component over a boundary. So gradient of u dot n over a boundary of omega. But the normal component of a gradient u dot n, that's the normal derivative. So this is the same as du dn. But du dn is specified to be equal to h. So we get minus integral over a boundary of h. So what that means is, so this integral of f over the interior must equals integral of h, or minus h really. There's a mistake in the notes that minus is not there. Okay, so this is called a compatibility condition. Now, this is rather unusual because normally, when you're specifying a problem, like an initial or boundary value problem or whatever, we have a PDE and you have some initial boundary conditions. Most cases, especially for equations that we'll study, you can specify whatever initial or boundary data or source terms or whatever you want, all independently of one another, and you'll have a solution. But this is an exception to that case because here, you can't just pick any old f and any old h and expect to find a solution. This compatibility condition must be satisfied or there's no existence even. So in fact, you never have a situation where it's a unique solution. Either there's no solution if a condition isn't satisfied, or there's infinitely many solutions that all differ by a constant if a compatibility condition is satisfied. Okay, this time you missed a fair amount. So any questions about that compatibility? All right. So that's all that I have on discussion of these known as elliptic equations. So we'll pull Laplace's equation, Poisson's equation. So now I'm going to shift gears to heat equation. And those of you, well, I guess all of you have taken at least a few classes with me, know that now and then I'm prone to forgetting to move a computer. So be prepared to remind me about that just in case I almost forgot that time. All right, heat equation. Now, first I'll say a few words about the derivation of the equation. Okay, so suppose I have some domain D, and working in n-dimensional space, and then I have some subset V of this domain. Now, Fick's law states that the flux of heat energy across a boundary of V. So, in other words, flux of heat energy crossing into actually. Be careful not to without a divergence theorem. So actually, leaving P, not entering, is defined by denoted by F, and it's equal to minus A times the gradient of U, where U refers to temperature, and A is a constant factor, but it's depending on the thermal conductivity. Now, by conservation of energy, really mass balance, what we get is the that the rate of change with respect to time of the total amount of heat energy within the subset V is equal to proportional to the flux. Hold on a second. Sorry, I just got great news, or nice news about a paper of mine. So. All right. Sorry, a little excited about that right now. Okay. Oops. Okay. Now, it's proportional to the total flux across the boundary of this subset. And since we're going across the boundary, we have to take the flux. We want the normal component of a flux, because that's indicates how much flux you're getting. Well, flux is, again, passing out through region, but then we negate it to indicate flux of heat energy going in. So that's why the minus is there. Okay. Yes. All right. Now, strange here. Nope, we're good. Okay. Now, by the Gauss divergence theorem, which I've applied earlier for something else, but now I'm going the other way, the normal integral of a normal component of a vector field is equal to the integral over the interior of the divergence of that vector field. All right. So now we have two integrals that are both over the interior. But now I'm going to use my definition of flux. So now my right-hand side integral, we're assuming that this domain V does not change over time. It's some fixed subset. So that d dt, I can just move inside the integral. And then I have minus V, and then divergence of S, so divergence of, well, right. Cut off again. Okay, so I was right here before. So here I just replaced F with its definition, minus A gradient to U, and then minuses cancel. So I have A and B. A is pulled out, so I have AB, which I'm just going to call C. And now what I have is the divergence of the gradient, but that is the Laplacian. Like that's where the notation gradient squared u comes from. So now I'm going to, and this is over v also. So now I'm going to write this as an integral, one integral, everything on one side set equal to 0. So this is saying at ut minus c Laplacian of u is equal to 0. So we know the integral of this expression is 0. However, I chose an arbitrary subset v of my domain D. And because this is true for any subset, if the integral of some function, this function, is equal to 0 over any subdomain, then it must be 0 everywhere. So this whole thing must be 0, therefore ut is equal to c Laplacian of u. So that is where the heat equation comes from. This is how PDEs are often derived. You have some physical laws, like Fick's law, and also conservation of mass or energy. And from those relationships, and typically using something like the divergence theorem, is how these kind of PDEs pop out. Okay. All right. Now, just as Laplace's equation had a fundamental solution, the heat equation also has a fundamental solution. I'm not going to take the time to derive the whole thing here. I might have done that in some other class, like either 417 or 606, I don't remember. Okay. So it's possible, depending on what class you've taken, you might recognize it. P of xt is equal to 1 over 4 pi t to the n over 2, where n is the number of spatial dimensions you have, e to the minus magnitude of x squared over 4t. Okay. So what's interesting is, on the one hand, as t goes to 0, it seems like you might have a problem here of dividing by 0, but at the same time, as t goes to 0 here, your exponent is becoming closer to minus infinity. And e to the minus infinity is going to 0 faster than that's going to infinity. So you still have a well-defined solution. Now, a fundamental solution satisfies the simplest form of the heat equation. Ut is just plain old Laplacian of u, so the constant c is equal to 1. And this is, again, a free space solution, and a t greater than 0. And we have initial data. I saw this last time. This is a Dirac delta function. So it's equal to 0 everywhere except at the origin, but it gets a distribution. So, all right. So, from this fundamental solution, we can use it to describe a solution to a more general problem. So, heat equation in free space. And then arbitrary initial data. So u naught of x it's a convolution of your initial data with the fundamental solution. And so it comes from the fact that if you substitute this into the heat equation, that phi satisfies it. But from the initial condition, if it lets t equal 0, then here you get a delta function, but the integral of a delta function times u naught is just going to give you u naught of x. That's why it satisfies the initial condition. Okay. Now, like Laplace's equation, heat equation also has a maximum principle. So I can define, so our spatial domain is omega. We'll see it's bounded. And then I'm going to define this domain omega t to be omega together with an interval, a bounded interval in time. So 0 up to capital T. And then I'm going to define the boundary of omega t to be actually not the entire boundary. So what you have is, like, if this is my domain omega sitting in Rn, so if you think of n equal 2 in this case, and then we add the time dimension to it. Whoops. So here we have omega t. Then the way I'm going to describe the boundary for our purposes is, first we have the entire domain omega itself, along with, so here's t equals 0, and here's t is equal to capital T. So upwards is your t-axis. So the whole domain omega, together with t equals 0, is one part of the boundary. And I'm also going to include the boundary of omega together with the interior of the interval in time. So in other words, the sides is the boundary of omega Cartesian product with every single t value between 0 and capital T, not including. So, in other words, in this definition of boundary of omega t, there's no lid. So the omega Cartesian product of capital T is left out. Okay. So now suppose we have this initial boundary value problem, IBVP, for a heat equation. For x and t inside our domain omega t. And then we have initial data. So this is initial condition. So x is in omega, t is 0. And then we have boundary conditions, a Dirichlet boundary condition. U is equal to g. And this is x, and so x is on the boundary of omega, and t is in the interior of the interval in time. Okay. So let's assume that the U is the solution of this initial boundary value problem. Then we have what's like in Laplace equation, a weak maximum principle. And that is that the maximum of U on the closure of omega t. So that whole domain, including boundary points, except for the lid, again, is equal to the maximum on the boundary, again excluding the lid. So just like Laplace's equation, you define the boundary appropriately, maximum occurs on that boundary. And then we have a similar strong maximum principle if a maximum value is assumed in the interior of omega t. That can only happen if u is just a constant function. All right, so it corresponds very closely to what we saw with a Laplace equation, and then the same consequences. So all this leads to a minimum principle and uniqueness. The proof goes exactly the same way. The difference of two solutions satisfies the same PDE with zero initial data and zero boundary data, therefore it must be zero throughout the whole domain. Okay, I have something else to get in here. Okay, I have to check something in the notes so I don't tell you something wrong. Okay. Okay. In the notes I say if we assume the boundary data is zero, that's not what I want. It's actually, well, oh. Okay, let me, have G for the boundary data. Oh, that's so weird. Okay. Yeah, the MIT notes did something rather strange with the notation, so I just have to be extra careful here. So consequences, this is one consequence, this is two consequences. Same consequences we had as for Laplace equation. But P equation, particularly, there's a third consequence that's of interest. And that is, let's suppose that, so I do need to fix something in the notes here, my notes. Okay. So let's suppose that the boundary data is zero. And let's suppose that the initial data is non-negative. Then the consequence of that is u has to be strictly positive throughout the domain. Now, there's an interesting description of this. That is, infinite speed of propagation. Now, you might be wondering, how on earth can we conclude something like that from this mathematical statement here? I'll give you an example. Let's suppose that our initial data is only required to be non-negative. So let's suppose u naught is actually zero. Whoops. Let's suppose that u naught actually is zero over most of the domain, except for some portion here where it's non-zero. Here I've drawn it to be a constant in between. So actually, who could tell me what this kind of function is called?
Kind of potential in quantum mechanics. Oh, the name of the function.
Yeah, the type of function.
I'm sorry, I just know the name of it in Persian.
Oh, characteristic function.
Yes.
Okay. Right.
Yeah.
What?
It's a hard way, but it was.
Oh, okay, that too.
Yeah.
All
That's
right.
what I was thinking too.
So if you know it looks like this, then the solution, even at the smallest instant, so it doesn't matter how, so t can be arbitrarily small, has to be strictly, like it might look like this, for instance, like slightly smoothed out. But the point is strictly greater than 0. So in other words, whatever heat, suppose if this is our temperature profile, if we don't have any heat energy out here initially, but as soon as the clock ticks at all, you have non-zero temperature everywhere. So it's not like an advection equation. If this were like a wave equation, if you had initial data like this, it would take time, a non-negligible amount of time for non-zero values to occur out here. But not with the heat equation, it happens immediately. So that's what's meant by infinite speed of propagation. All right. Well, actually, this is a sensible breakpoint. So when I come back, we'll see our picture for a while longer. I'll go back. I'll discuss the wave equation, in fact, to show that contrasting behavior, which is very interesting in its own right. Okay. I actually have one more item related to the heat equation before moving on to the wave equation. So, for the inhomogeneous heat equation, so UT is equal to Laplacian of U plus F. So F represents like an external source term. It can be a function of, I'll write explicitly, x and t. And for simplicity, I'll assume the initial condition is 0. And this is for free space solution, so no boundary conditions. Okay. Then the solution has an interesting form. Because if I take, I'm leaving space here deliberately, keep that in mind. If I have this integral, which is similar to something I wrote before, because this is the general solution to a free space problem, except it is shifted in time. Now, so before I fill in the rest of this, this is a solution of the homogeneous heat equation, and U of x s is equal to F, the same source term, evaluated at t equal to s. So it's like this is playing a role of an initial condition, except it's not at t equals 0. It's at t equals s. And the fact that we're shifting the t variable here by s. So when t is equal to s, we're using a fundamental solution at time 0. So that's why it's a solution to that. But then what we do is we take that solution. So the source term is like it's feeding in initial data at every single instant. And then what we do to take all of those into account is we integrate that from 0 to t ds. So the solution of a inhomogeneous problem with zero initial data is the same as the integral of the solution of a homogeneous problem with the source term as initial data at every single instant and integrate over all those instants. This is called Duhamel's principle. Now, for a more general problem, like suppose you had non-zero initial data here, what you would do is you would use the solution of the homogeneous problem with your non-zero initial data, and you just add it onto this. So it's not really interesting. Now, even though this is some fancy principle, Duhamel's principle, that's stated for PDEs, the reason the solution is equal to this actually has its roots in first-order ODEs. Because so all to the side, if I work out this problem, y prime is equal to ay plus b of t, and I'll propose initial condition y of 0 is equal to 0, then solving this using kind of techniques you learned in like Math 285, what you get is y of t is equal to integral from 0 to t of e to the a t minus s b of s ds. So I didn't go through the whole process here, but if you use that technique you learned in that kind of class with your integrating factor and so forth, and you make sure that the initial condition is satisfied at 0, feel free to work it out yourself to convince yourself. This is what you get. And notice, again, integral from 0 to t, and this is a solution of y prime is equal to ay, y of s is equal to b of s. So now the source term is again treated as initial data, but at every instant, and we integrate from time 0 to the current time. So these two correspond very, very closely. So in fact, Duhamel's principle could likely be proved using an approach like this for ODEs. Okay. The fact that we're adding all of these solutions together by integrating from 0 to t, that's an example of what is called superposition. There are many different forms of superposition, like for instance, taking solutions corresponding to different initial data and adding them together if you add the initial data together. But this is a different form of superposition where, again, we're, in a sense, summing up all of these effects. Okay. So what's interesting is, suppose this source was only equal to non-zero up until a certain time. Then what would happen is you would only really need to integrate up until that time when f is non-zero. But as time continues, this part's still going to change. So whatever initial data you have, whatever non-zero behavior you had in your source, affects the solution for all time. But you only need to integrate over a portion where your source term is actually non-zero. Okay. So time-dependent problems in general have this Duhamel's principle to explain how to solve non-homogeneous equations in terms of homogeneous ones.
Did we learn about that in 606?
Probably, yeah. I'm not sure if I gave it by that name. You definitely covered some certain non-homogeneous problems.
Yeah.
Yeah. Okay. Yeah, I should have said it back then. That was such a long time ago. Yeah. Well, really, the first part of this class, actually up until through this next section we're going to do, is kind of a nice 606 review. Of course, not all of you took 606. Well, 1, 2, 3. You meant to, but it got canceled that year.
Did you get
I'm sure we offer, but I don't expect to teach it, or don't want to teach it really. But
What class?
606.
Oh.
Yeah, I'm guessing Dr. Tian will be teaching it. All right. Now, two related equations dealing with advection. So, first the transport equation. So ut plus a vector b, which is called direction field, dot product with the gradient. So you think of this as really the derivative of u in the direction of b. We'll call this a direction field. Is equal to 0. And this is a free space problem, no boundary conditions. And then we have an initial condition. Okay. Now, I'm going to assume that B is a constant vector, not changing in time, or space for that matter. So, in this case, we've actually seen a one-dimensional version of this, like ut plus ux is equal to 0, and the solution turned out to be a shift. So it's actually the same idea in higher dimensions. So the solution is u naught x minus t b. So in other words, the initial data is shifting in the direction of b. And in fact, so actually you can confirm this using the chain rule. So du dt would be u naught, gradient of u naught, evaluated x minus tb, and then dot product with the derivative of this with respect to t. So that's going to be minus b. So sure enough, we have minus b dot product with the gradient of u. So in other words, ut plus b dot gradient is equal to 0 as it's supposed to be. All right, so here I'm just verifying that this is the solution. Okay. All right. Now, let's look at the corresponding non-homogeneous problem. Or notice I call it an inhomogeneous problem. Non-homogeneous, inhomogeneous, whatever. Where we just add on a source term. So ut plus b dot gradient is equal to f, and still some initial data. Okay. Then I can write down a solution to this using that solution over there and Duhamel's principle. So that tells me that u of xt, and this is actually what I was talking about earlier. In the previous instance of Duhamel's principle, I had the initial data being 0, and I said if it was non-zero, you just had another term to add on. And that's what you do here. Your first term is the homogeneous solution. Then, the part that actually comes from Duhamel's principle, integral of, and now you're treating your source term as your initial data. So it'd be f of x minus, instead of just t, you'd have t minus s. So you always have that shifting going on in your integrand, at least for the x variable. And then you have s ds. Okay, so this is a solution of ut plus b dot gradient of u is equal to 0, u of xs is equal to f of xs. And so we just integrate all of those solutions. Okay. Now, the reason why I'm introducing the transport equation, my real goal is to solve the wave equation. All right, so a wave equation, unlike a transport equation, which involves only first derivatives in both space and time, wave equation involves second derivatives in space and time. So we have utt minus Laplacian of u is equal to f. So what I'm going to do is I'm going to scale down to a simpler version of a problem where we're just in one space dimension, and we'll start with the we'll deal with a homogeneous case. So 1D will have utt is equal to uxx, and this is in free space. X is not a vector now. And then we have initial data. Now, because it's second order in time, we actually need two initial conditions. So here's our typical mutual initial condition on u, and then we have a condition on the first derivative with respect to time. H of x. All right. Now, what I'm going to do is, actually, I'm going to write the PDE this way, set everything equal to 0. And that allows me to write this. This is all, I can only do this because we have constant coefficients. I can write the PDE in factored form. So I have partial with respect to t plus partial with respect to x, partial with respect to t minus partial with respect to x of u is equal to 0. So in other words, so you can think of this as differentiation with respect to t squared minus differentiation with respect to x. That operator squared, the squaring of operators. Well, just like other squares, you can think of this as a difference of squares, so I can factor it that way. So these are differentiation operators with respect to t and x. And what that lets me do is solve this equation, break down a transport equation, break down a wave equation into two transport equations. So I can use my transport equation solution from over there. So what I'm going to do is, I'm going to define this part, so dt minus dx of u, I'm going to call that v of xt. So that would mean that I have this, so wave equation breaks down these two transport equations. I have vt plus vx is equal to 0 because this applied to v is 0, and ut minus ux is equal to v. So I have this homogeneous transport problem, which I know how to solve, and this non-homogeneous transport problem, which I also know how to solve. So first, from this transport equation, I have this is some function as yet unknown solution is some function a of x minus t. Because if I take the derivatives of this with respect to both x and t, I'll get at plus ax is equal to 0. I don't know what a is yet. That'll be determined by these initial conditions, so we'll come to that later. Okay. Now, I could use that in here. So ut minus ux is equal to a of x minus t. So, so again, I have a transport equation, so I can use my transport solution, the non-homogeneous case over there, where in this equation, my direction field was just equal to 1. In this case, my direction field is equal to minus 1. So I can take that into account in using my solutions over there. So what I get is using that non-homogeneous solution on the previous board, scaled out to one dimension, and with b equal to minus 1, I get u of xt is equal to, now the first term, no, if you look over there, is u naught. That's my initial data. So that's what I'll use here, this initial data. G of x minus tb, but b is equal to minus 1, so it's x plus t. And then I have my integral, and now notice what goes in the integral over there. It's f. It's your source term. Well, this is my source term, so that's what I'm going to use. So I'm going to have a of, and I'm going to have x. So in the previous solution, x gets replaced by x minus t minus s times b. But b is equal to minus 1, so I'll fill that in. And then t gets replaced throughout by s. So this minus here becomes a minus s. And then, actually that's all I have. Okay. ds. Okay. So, so this plays a role of f of x minus t minus s times b s, where in our case b is equal to minus 1. So this x explains this part, and then the fact we're plugging in t here explains how we get this down here. All right. Now, that integral is kind of messy. So what I'm going to do is I'm going to make a change of variable, or as you know from Cal 2, a u substitution. So I'm going to, in order to get a simpler integrand, okay. So I'm going to let, what I want to do is I want to map the interval 0 to t that I'm currently integrating over to interval x minus t to x plus t. So I just want to do the simplest change of variable I can find that will do that kind of mapping. Okay. Now, the way I can do that is, okay. So if this is s, and I'm going to call this, you can use y to refer to my new variable. So what I need to do to s, notice this interval is centered at x, but this interval is centered at t over 2. So I need to, well, what I'll do first is take s, subtract t over 2. Because that way the interval is now symmetric. It goes from minus t over 2 to plus t over 2. Then I need to divide by the size of that interval, which is t. So now it's going from let's see, it's an interval with 1, so it's going from minus a half to plus a half. Now I need to multiply by the new size of the interval, which is 2t. So now going from minus t over 2 to or minus a half to a half, and going from minus t to t. But then I want the interval centered at x, not 0, so I add on x. Okay, so now I need to simplify this as much as I can. The t's will cancel. So this is going to be 2s minus t plus x. It's a good idea to confirm that this really works. So if you plug in the endpoints, your original endpoints, 0 and t, you should get x minus t and x plus t. For instance, if I plug in s equals 0, I get x minus t. If I plug in s equal to t, I get x plus t. So it works. And I'm actually kind of surprised I did it right. Because for some reason I don't have it written down here. Because I was feeling lazy or tired when I wrote these notes. Okay. Now, that means that dy is equal to 2 ds. So that means that my new integral is going to be multiplied by a half. So the other thing is, when I make a change of variable in my function a, I have x minus t minus s times minus 1 minus s. Well, if I write that out, I'm going to have minus, 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 that's a minus, x minus t minus 2s. Okay. Something does not look like how I want it. Oh. I think I know what happened. But no, oh. Yeah. Plus t, which is still not exactly what I want, because yeah, it was supposed to be just reduced to y. Okay. So I'm not sure if I was supposed to do like a reflection or something. Okay. If t is equal to 0, then I get, yeah, x minus t. And then you get x plus t. So 2s is equal to so 2s is equal to y minus x plus t. minus y plus 2x, which is definitely not what I want. Frustrating. Okay. I think if I make this work like a reflection, then it'll work out the way I want. Okay, so instead, yeah, because I put a minus here, and everything else is kept the same, then I get minus 2s plus t, then dy is equal to minus 2 ds, and then this turns out to be equal to y, which is what I really want. Okay. And then my integral from 0 to t of a of x minus t minus s times minus 1 minus s ds becomes minus 1/2 integral of a of, now all of this now is y, dy. But now, if I plug in my limits, so I plug in t equals, s equals 0, I get x plus t, and then x minus t. So it seems like the limits are in the wrong order. But then I just flip the limits and get rid of a minus. And now I have, finally, what I want. Okay. So, moral story, when I do a substitution in my notes, write down a bank substitution. So, I could have seen it by just looking, okay, well, I want my a of all that junk just to become a of y. Because the whole point of a substitution is to make the new integrand as simple as possible. Okay, did I catch all of that? Not entirely. Okay. All right, so now if I look at my overall solution, after making a change, so u of xt is now g of x plus t plus 1/2 integral of x minus t from x minus t to x plus t of a of y dy. Now, the thing is, I need to account for the other initial condition, because this satisfies the condition. If t is equal to 0, I have integral from x to x, that'll be 0, and I'll get g of x like I'm supposed to. But I need to enforce the other condition. Du dt of x0 must be equal to h of x. So what I'm going to do is I'm going to differentiate this with respect to t, and then substitute t equals 0. So du dt of xt is equal to g prime of x plus t times the derivative of what's inside with respect to t. That's just 1. Plus 1/2, and now I'm differentiating an integral with respect to t where t is in the limit. So that's where you use the freaky part of the fundamental theorem of calculus, and I get a with the upper limit plugged in times the derivative of a limit with respect to t, but that's 1, minus integrand with the lower limit plugged in times the derivative of a lower limit with respect to t. But now I need to substitute t equals 0. So du dt of x0, which is supposed to be h of x, is equal to g prime of x. And then over here, I plug in t equals 0, and I get a of x minus a minus, so plus a of x again, over 2. So I just get a of x. So now I know what a of x is. So a of x is just h of x minus g prime. So now I can use that in here. So now what I'm going to get is of x plus t. And then I'm going to handle just this term first, separately from the other. So I have 1/2 integral x minus t to x plus t h of y dy. And I don't need to do anything more with that. That term is done. And then I have minus 1/2 integral x minus t to x plus t of g prime of y dy. But I'm integrating a derivative, so that cancels out. So all I have to do is this is equal to minus 1/2 g prime, so g of x plus t minus g of x minus t. So now what I can do is I can combine this part in brackets with the g of x plus t that I have over there. And finally, I can write down the solution in its simplest and possibly familiar form. So u of xt is equal to 1/2 g of x plus t plus g of x minus t plus 1/2 integral x minus t, x plus t, h of y dy. Which is the inverse solution. Okay. I was going to say, who can tell me what that is, in case you remember from 606, but I figured someone would just look it up in the notes. So, never mind that. Okay. So any questions about how this solution came about? Trevor Freaky. Okay. 10 minutes left. Oh, I might be able to get through the rest of this. So I can finish the chapter, and then tomorrow, this numerical methods for PDE course can finally get into numerical methods. Okay, now, this is one dimension. 3 dimensions. It seems kind of weird to skip from 2 to 3, but there's a reason for it. So we have UTT minus Laplacian of U 0, and then we have U of x0 equals g of x. Same initial conditions, just written for 3D. And no boundary conditions. The solution is obtained by what is called Kirchhoff's formula. Although I've actually seen this formula written differently last time I taught about this a long time ago. So it's written as integral over the boundary of a ball centered at x with radius t. And the integrand is written in terms of the initial data. Often the way I've seen it is written in terms of average values of certain functions over the boundary of the ball, centered at x with the radius t. Okay. So that's the 3D case. And the 2D formula is actually derived from this by projecting the boundary of the ball of radius t in 3D onto the corresponding ball of radius t in 2D. So it's like if you're taking like a hemisphere, or you're basically taking a whole sphere, just the shell, the boundary of it, and smashing it down onto the xy plane. So in 2D, the approach which I covered in much greater detail in, I think it might have been 417. The method of descent. Remember in my notes I had it all written out there how I did it. And you get a formula that's called Poisson's formula. And u of xt is 1/2 integral over the ball, not the boundary, but the entire ball, so including the interior. And the numerator is similar to the integrand that you had in the 3D case. Well, there are certain differences. Plus t radiant of g dot x minus y, but now you have this denominator, which kind of comes from Pythagorean theorem in a way. dy. All right. Now, the difference between these two is very significant. Whoops. And I want to give a contrast. This is something that numerical methods have to take into account because they need to produce the same behavior in their solutions. So, as an example, I'm going to let g of x equals 0. That part of initial data is gone. And then h of x equal to the Dirac delta function. So then I can write down the solutions of the 2D and 3D problems. So in the 3D problem, what ends up happening is, so all the terms in the previous solution for 3D case, these terms drop out. We're left with a delta function. And the t is a constant. That could be factored out. Okay, so what you get is u of xt is equal to t times the integral over the boundary of the ball of center x radius t, delta of y, and what you get is, in the case where the magnitude of x is equal to t, you get 1 over 4 pi t. Where that comes from, it is t divided by the surface area of a ball of radius t. The surface area of a sphere of radius t is 4 pi squared. But you're dividing t by that. And then 0 otherwise. Okay. So, how this solution behaves is, suppose x, you're at a fixed point x. You want to know how the solution behaves at that particular x. Well, originally, your magnitude of x is positive. It's not equal to t, because t is starting out at 0. So, t starts marching forward. Your solution is 0. It stays 0 until all of a sudden t is large enough so that it's equal to the magnitude of your point, and you get non-zero. And then it goes back to 0 again. So what we get is a sharp front. If you were to visualize the solution in the whole space, you would start out with just kind of like a point source, and then you'd have this expanding sphere in 3 dimensions, where the solution is, and only on that sphere, the solution is non-zero. And that keeps expanding, but once that sphere passes, then the solution goes back to being 0 again at all points inside. So that's the behavior you get in 3D. But in 2D, your solution, if I were to let g be 0, and h is this delta function, is an integral over the whole ball, including the interior. and I get t squared delta function over t squared minus that. And how the solution behaves in this case, if the integral were to be worked out, it would be, this integrand, 1 over 2 pi t squared minus x squared 1/2, whenever x is less than or equal to t, and 0 otherwise. So if you were to analyze the behavior solution in the same way, at a particular point x, at first it's 0. It stays 0, and then once the t is large enough so that it equals the magnitude of your point, then the solution becomes non-zero and stays non-zero from then on. It's not a sharp front. So now what will happen is, as t gets larger and larger, the solution will decrease towards 0, but it's entirely different behavior than what happens in 2D. This relates to what's called, I'm going to pronounce it wrong, but Christian Huygens principle, that this kind of behavior we see in 3D happens for odd dimension, greater 3, 5, and so on, not dimension 1. And this is what you see in even dimensions. So very interesting how the number of dimensions that you're in affects the behavior of a solution so drastically. Okay, so that is a nice 3-day overview of PDEs in 1, 2, and 3D. So tomorrow I can start with finite difference